In this video, I'm going to show you how to implement regression trees in R. So we're going to need a couple packages. If you don't have them already, you're going to need to install a couple packages. So we're going to install rpart. Okay, so I obviously already have it. So that's not going to work for me, but for you, you might want to pause the video and make sure that it installs properly. And next, you'll install this package, which has a similar name. And this package, what it will do is actually give us a visual flow chart of a tree. Remember, regression trees are a very visual kind of transparent machine learning algorithm. That's one of their advantages. So this package will actually help us plot it. Okay, so after you install both of these packages, of course you should require them into the current environment. So I'm going to require this and basically load these packages. And once I have these packages loaded, I'm going to choose a data set that's available to us all. So if you go under data, you see we have a bunch of data sets here available. I chose a data set here labeled mammal sleep, so it's called msleep. If we go alphabetically, okay, it's split up into the different packages here. So here it is. It's in the ggplot2 package. So if you want this data set, you can download this package, which is another package that you should probably learn and have as well. So once you have that package, you'll see the msleep data set. So if I just load msleep, this is for purposes of illustration only. So let's look at the structure of this data set. We have 83 examples and 11 variables. So, and here are the variables. Now, I modified this data set considerably. And how did I do this? To save us time, I prepared the data to kind of eliminate variables that I was not interested in. And so if you run this code here, we're going to create a new data frame which just takes a subset of these variables and just takes the variables I'm interested in. So if you run that code and you actually look at the structure of this new data frame we create, you'll see we still have 83 variables, 83 observations, but only 4 variables. So here are the variables. Vor is a nominal feature which tells us whether the mammal, is a carnivore, an omnivore, an herbivore, or an omnivore. I guess that showed up twice. That's not my mistake. I'm not sure exactly what that's saying in the data, but that is a fourth at least. Oh, sorry. These are not the levels, rather these are the first few observations. So the first mammal was a carnivore, second was an omnivore, and so on. Then we have sleep total. That's actually what we're going to try to predict here. So that's our target feature for this little example. So let me actually clean this up here a little. So sleep total is our target feature. As you can see, it's numerical. So these are the number of hours that the mammal sleeps. The brain weight, also numerical. We have some missing values. It shouldn't be a problem. And body weight. Okay. Not sure if that's in pounds or whatever it might be. So, but that's not really important to us. Let's take also a little look at the data set here. Here are our features, and here are first few observations here. So, first mammal was a carnivore, sleeps on average for 12.1 hours. We don't know their brain weight. We do know their body weight is 50, and so on and so forth. Okay, it might not be a bad idea to recode this vor variable as a factor. Right now it's coded as a character, but it should not affect us in what we're trying to do here. Okay, so what we want to do is we want to build a decision tree, specifically a regression tree, that will predict the total sleeping hours of mammals based on the other variables available to us, which we just examined. So how do I do this? Well, I'm going to load the rpart package. I'm going to use a function in that package called rpart. And this is basically a way to define the function. So first I have, it works very similar to the lm function. So first I specify my target feature. In this case it was sleep total. And then using the tilde, I specify my predictors. If I put a dot that says include all other predictors, or at least try to include, see which ones are useful, most predictive, and include only those. Okay. The data set is df, which we just created. It was a simplification of the msleep. And the method we're going to use here is ANOVA. And that is because our target is a numerical feature. So if I hit enter here, I'm going to get a lot of output. Typically, if you specify a model, you should name that model something. So I use the convention of M1, M2, M3, M4 to keep track of my models. So I'm assigning the name M1 to this regression tree model that I'm creating here. Hit enter, no error messages. That's a good sign. If I actually type M1, I'll see a depiction of the regression tree. So we have the root node here, and then we have some branches here, and then some sub branches, and then sub branches, and sub branches, and so on and so forth. And each of these has a load of information. You can see this legend over here. So just very quickly on some of this output, we started with 83 observations. That's not a surprise. We split the data first on the body weight. So of the features that were available to us, body weight was the most predictive. So we split mammals that weighed more than 167.947 went one way. Mammals that weighed less than 167.947 went the other way. You see 9 weighed that, and 74 weighed less rather. And so the tree continues to split and split and split. These asterisks indicate leaf nodes, so you have to know a little bit about regression trees and trees in general. So trees have a root and decision nodes, and then finally leaf nodes. To actually visualize this, we can use that package we installed earlier called rpart.plot. And if you specify a few options here, you will get a decent looking plot here. So let's say show us 3 digits and make all the leaves drop to the bottom. Okay, and we get a little plot here. If I run this again, you'll see it cleans up a bit. So here we start at the root, okay, and we split based on body weight. Okay, so greater than 168 goes this way. And this 3.49, that's the predicted number of sleeping hours for mammals that have a body weight of greater than 168. Okay, if the body weight is less than 168, we go this way. And then we don't have a prediction yet. We don't have a final prediction yet. We have another split. We split a little finer on body weight. So those that are greater than 1.85 go this way. Those less go this way. Okay, and then so on and so forth. Next, herbivores go this way, and the prediction is 6.64 hours. Okay, and if your body weight is greater than 1.85 but less than 168, you're here. And if you're a carnivore, insectivore, I guess, or omnivore, you're going this way. And then if your brain weight is greater than 0.1376, you go this way, and so on and so forth. All these lead eventually to a leaf. So down here, we have all the leaves. Up here, we have the root. These in-between decisions, you can call them decision nodes. Sometimes you'll see there are actually nodes drawn here at these decision nodes, and sometimes just for fitting everything into a tight space, those are left off. Okay, so you see first off that we have all the predictions down here, and these are the predictions. Okay, and those predictions, by the way, are arrived at by taking the average of the target feature, which was sleep total, at this particular subset of the data, or for this particular subset of the data. So for example, mammals that weighed less than 168 but more than 1.85, but here, let's do it this way. Mammals that weighed less than 168 but more than 1.85 that were herbivores. Okay, in a sense, this path that we just took here was we made 3 slices of the data, or subgroups of the data, and we finally got to a subgroup down here. And that subgroup, if we were to average the sleep total variable for that subgroup that satisfied all these decisions that we made, it would be 6.64. Okay, and by the way, this percentage here, this 8.4, that's just telling us that 8.4% of the total number of observations ended up in this node. If you add these guys, they should add up to 100%. Okay, so that's how you read a regression tree. If you come back here to the original output, which was not as pretty, it's the same idea, and they use indentation instead of actual visual, like we just saw, to depict the order of the decisions and the flow, and these asterisks correspond to the leaves in this plot. Okay, so that's the connection between this output and this. Now, something you might want to do next is to actually make some predictions now. So we trained the model, we trained the regression tree model, but now you want to use it to make some predictions. So because I don't have a test data set, and I started with a really tiny data set to begin with, I didn't think of splitting the data. So let's just pretend that our training data will serve as also our test data. That's definitely something you don't want to do in practice, but for just so I can show you the functionality, I'm going to now use the same data that I used to train this model to make some predictions. Okay, so let's call these predictions P1, and then let's use the predict function. I'm going to predict with M1, which was the model I created up here using rpart. Okay, and the data set that I'm going to use for predicting, the values that I want to predict for are the same that I used to train, so I'll just use df here as well. Okay, if you had a test data set that you originally split, you would put the name of that test data set here. Okay, so maybe in the very beginning you split your data into a training and a testing data set. So here you would put your testing data set, whatever you called it, and up here you would have trained with just your training data set. Okay, that's the best practice, but that's not really the point of this particular video. So let's just predict for the training. So you see, if I type P1 here, you're going to see all the predictions for the 83. Okay, so these are all predictions here, and I have 83 of them. Okay, and then you see I have 83. Okay, now one thing we often want to do is to get a kind of assessment of how the algorithm is performing as far as accuracy. So there are many ways to do that. One way to do that, if you have a numerical target feature like we have, is to calculate the mean absolute error. Mean square error is another choice. Okay, there are other choices. So I'm going to do mean absolute error. So I have to write a function for this. So this is maybe a bit of an aside, but all mean absolute error is going to do is compare the predictions to the actual values for the target features. Take the absolute difference between them and then average that absolute difference. Obviously, a lower number would indicate a better fit. So I'm just writing a function that's going to do that. So I see I'm taking the mean of the absolute differences between actual values and predicted values. Okay, let's close the right number of parentheses here. Okay, so I've created this function. Now in order to use this function, I have to be careful. It takes 2 inputs. That's how I defined it. Okay, there's other tutorial videos I've created on writing functions. For purposes of this video, you can just copy the code here and use this code and create this function. Okay, but this function has 2 arguments we need to specify. So the actual values are can be extracted by actually going to the original data and looking at the sleep totals. And the predictions we just called P1. Okay. And let's see. Okay, we get an error here. Why is that? I see what I did here. I put a comma instead of a subtraction. Okay. Little typo there. So let's just fix that and then go right back up and compare, and we see that the mean absolute error between the actual values of my target feature and the predicted values of those very same examples is 2.42865. Okay, so is that good? Is that bad? I don't know. I don't have a frame of reference here, but if we were trying to construct a good prediction model for this data, I would compare the mean absolute error between the various models I run and obviously choose the one that has the lowest amount of error. Okay? So I hope this was helpful. It was very quick, admittedly, but we tried to focus on implementing a regression tree using the rpart package, plotting that regression tree, understanding regression trees in general, just very high level, and then finally giving an assessment of how the prediction process went. What we left out was a detailed discussion of how these splits are created by the algorithm or decided by the algorithm, how the tree decides to stop growing, a detailed discussion on how functions are written. That's not something I wanted to focus on, although we did need to create this function to assess how the whole process went. Okay, so I hope that was short and sweet and to the point. To fill in the other details, watch some of my other tutorials where I spend more time in those kind of directions. All right, I hope this was helpful. Have a great day, and be sure to watch my other machine learning tutorials on topics ranging from regression trees, classification trees, KNN, association rules, Twitter mining, social media mining, data visualization, regression, multiple regression, logistic regression, etc. All found on my channel.